Hello everyone, welcome back. In this video we'll be taking a look at Cauchy sequences. So what are Cauchy sequences? So a sequence AN is called Cauchy if for all epsilon greater than 0 there exists an n such that for all m greater than n greater than capital N, am minus n is less than epsilon. So let me restate the definition of what is a convergent sequence first to see the subtle differences between the convergent sequence and a Cauchy sequence. So a convergent sequence is basically the same thing, but it says for all epsilon greater than 0, there exists an n such that for all n greater than n, an minus l is less than epsilon. So basically, the only difference we see for Cauchy sequences is right here, where we have am minus an. So I want you guys to note that am and an are both elements, or they're both terms in the sequence. So let's take a look at this visually to see really what's happening here. So we have this sequence right here, and it converges. So a sequence is Cauchy if the distance between any two elements after some certain n, just like as we had for convergence, after a certain n, all sequences, for example, this is am and this is an, the vertical distance, remember, not the horizontal one, the vertical distance, the am minus an is less than epsilon. And this doesn't only matter for consecutive terms, it's for all terms after n. So for if we choose this term right here as am, and we choose this term right here as an, sorry, this should be an. So the vertical distance between this term and this term should be less than epsilon. So that's what basically a Cauchy sequence is if two elements after some certain n, the distance between the two elements is less than epsilon. So if you notice the difference between this Cauchy sequences and convergent sequences, for convergent sequences the distance between any term and L, and the limit L is less than epsilon. For Cauchy sequences, it's any two terms is less than epsilon. So let's take a look at this theorem. This theorem states that a sequence converges if and only if it is Cauchy. So any convergent sequence is a Cauchy sequence, and any Cauchy sequence is a convergent sequence, just as we saw from that visual graphically we saw before. We can't really draw a Cauchy sequence without it looking like a convergent sequence. So any sequence that converges is automatically Cauchy. So let's take a look at how to do the proof of this. So remember that this is a if and only if theorem, therefore we have to do two directions, because if and only if is denoted by the two directional arrow. So I have to prove both the directions. So before we dive into the proof of this, I want you guys to know that Cauchy sequences are bounded. So remember that Cauchy sequences are convergent sequences and convergent sequences are Cauchy sequences. So Cauchy sequence, and we know that convergent sequences are bounded. So Cauchy sequences are bounded also. And the proof of this is very similar to the proof of how we showed that convergent sequences are bounded. The bound M of a Cauchy sequence is also the maximum of the first elements x1, x2, and x3 all the way up till xn plus 1. So if you guys are not comfortable with this proof, I suggest you go back and watch the video of bounded sequences. Well, because the proof of how Cauchy sequences are bounded is very similar, with some few differences, such as instead of L plus 1 we have xn plus 1. So no, Cauchy sequences are bounded. So let's go on and prove this main theorem that says a sequence converges if and only if it's Cauchy. So we're going to do the first direction first. So when we're doing the first direction, we can assume the first part of the statement. So we're going to assume that the sequence converges. So assume the sequence converges. So now what do we need to show? So we need to show that the sequence is Cauchy. We need to show the sequence is now Cauchy. And Cauchy is a name of a famous mathematician and who got this sequence. So we need to show the sequence is Cauchy. So assume the sequence converges, we need to show a sequence Cauchy. So we need also to show that a sequence is Cauchy. From the definition of Cauchy sequences, we need to show that xn minus xm, where xn, okay, let me put this as xm and this as n, because that's what let me write that again right there. Xm minus xn is less than epsilon. So we're going to do the age, or so assume the sequence converges. So we know that this xn converges to certain limit L. So we're assuming that. So we're going to do the mathematical trick we've been doing before of adding and subtracting L. Right, so this can be written as, by the triangle inequality, again, this can be split into L plus L minus xn. And I want you guys to note that L minus xn is exactly equal to xn minus L. It doesn't matter though, however we write it. And since we know the sequence converges, we know since we know the sequence converges, we can make xn minus L as small as we like. So I'm going because so there exists an n, we can make it as small as we like. So we can make it less than or equal to whatever we want. So I'm going to make it less than or equal to epsilon over 2. So note that xn and xm are both terms of the sequence x, are both terms of the same sequence. So we get that this is less than epsilon over 2 plus epsilon over 2, because we can make it as small as you like, and this just adds up to epsilon. So we get that this xm minus xn, we get that xm minus xn is less than epsilon. And we're done with the proof of the first direction. Now let's go on and prove the second direction. Hopefully it'll fit in this space. Let's go for a different color there. So the second direction, the opposite direction. So when we're proving the opposite direction, we're gonna assume the sequence is Cauchy. Assume the sequence is Cauchy. So since it's Cauchy, xm minus xn being less than epsilon is true. So we need to show the sequence converges. We need to show the sequence converges. Right, how can we go about and doing this direction? For this direction, we started with the Cauchy sequence, and we know that Cauchy sequences are bounded. So we'll use the Bolzano-Weierstrass theorem that we did in the previous video to produce a convergent subsequence. So we're going to produce a convergent subsequence of this sequence. So the subsequence, we're going to denote it by xnk. and this subsequence, we're gonna say the limit of this subsequence. Since we know that Cauchy sequences, since we're assuming the sequence is Cauchy, and we know that the Cauchy sequences are bounded, and the Bolzano-Weierstrass theorem guarantees that every bounded sequence converges to a limit to some. The Bolzano-Weierstrass theorem guarantees that every bounded sequence has a convergent subsequence. So therefore, this sequence xn has a convergent subsequence xnk that converges to a limit x. So the idea is to show that the original sequence xn converges to the same limit. So once again, we're going to use the triangle inequality argument to show that we can do this. So since we know the sequence is Cauchy, we can make this sequence be less than whatever we like. So there exists some n. So this sequence is Cauchy for all epsilon greater than 0, as we saw from the definition. So xm minus xn is less than epsilon, and it's also xm minus xn is also less than epsilon over 2. And so is it less than 2 epsilon. We can make it as small as we like. We can make it less than whatever we want. So we can also say that since we know x and k converges to some limit x, we can make it as small as we like. We can say x and k minus x is also less than epsilon over 2, since we're guaranteed that it converges to x, so we can make it as small as we like. So we're going to say that is less than epsilon over 2. So we need to show the sequence converges, and to show that a sequence converges to a certain limit, we need to show xn minus x is less than epsilon. So I'm going to write xn minus x as xn minus xnk plus xnk minus x, and this is less than or equal to xn minus xnk plus xnk minus x. Now this is less than. Now if you see this, xn minus xnk is just is less than epsilon over 2. Well, why is this? This is because we assume the sequence is Cauchy, and since the sequence is Cauchy, any two terms xn and xnk are less than epsilon over 2. So xn minus xnk is less than epsilon over 2, and xnk minus x is less than epsilon over 2, because we know that x and k is a convergent subsequence, and we just wrote it right here that x and k x and k minus x is less than epsilon over 2. So this adds up to give us epsilon. So finally we get that xn minus x is less than epsilon, and that's what we needed to show. To show that a sequence is convergent or converges, we need to show xn minus x is less than epsilon. So we've shown both the directions and we've proved the theorem. So let's take a look at one more example of Cauchy sequences before we end the video. So consider this example. So we're told to show that this is, so we have to show that this sequence or this series converges to a finite number, right? How can we do this? To show that, so remember we have various strategies to show that a series or sequence converges. Firstly, we can find the limit, or else we can show that it's monotone and bounded, and therefore we're guaranteed that it converges. Or now we have a third strategy. We can show that it's Cauchy, because every Cauchy sequence converges. So let's go ahead and prove this. So for all epsilon greater than 0, there exists an n such that am minus an is less than epsilon whenever m is greater than n greater than capital N. Well, this is the definition of the Cauchy sequences. So we're going to do the sleepwalking part of the proof, the template part of the proof. So let epsilon be greater than 0. We seek n such that sigma n, or this should be 1, k equals to 1 over 1 over k squared, converges. Therefore it's Cauchy. So I'm going to say choose n equals to 1 over epsilon. I got this from doing my scratch work. I'm not going to do my scratch work here because it's pretty simple. You guys can figure it out on your own right now because it's really trivial. So am minus an or xm minus xn is the same thing. E is the same as sigma m and k equals to n plus 1 or 1 over k squared. And now this is less than sigma m where k equals to n plus 1 over 1 over k minus 1, because we know that because 1 over k squared is less than 1 over k minus 1, because the denominator is smaller, and when the denominator becomes smaller the fraction as a whole becomes bigger. So this fraction is bigger than this. So now we can write this as, we're going to substitute the n. So we will get 1 over, I'm just substituting the n right here. So you get n plus 1 and n. So I'm substituting n plus 1 into this. So, and we're going to do the same thing for n plus 2 until we go up till m. We're going to keep on substituting n plus 1, n plus 2, n plus 3 until we reach m right here. So n plus 2. So before we go ahead and do that, so this is the same as sigma m k equals to n plus 1. I forgot this step right here. 1 over k minus 1 minus 1 over k. K minus 1 minus 1 over k. Because 1 over k 1 over k minus 1 is the same as 1 over k minus 1 minus 1 over k. So I forgot that step right there. So we're going to repeat the same thing. We're going to substitute n plus 1. So we're going to firstly get 1 over n plus 1 minus 1 plus 1 over n plus 2 minus 1 all the way up till 1 over m minus 1 minus, so I substituted n plus 1 into this first fraction right here. Now I'm going to substitute it in the second fraction. So we'll get 1 over n plus 1 plus 1 over n plus 2 all the way up till plus 1 over m minus 1 and plus 1 over m. So this we can simplify this into 1 over n plus 1 over n plus 1 to plus 1 over m minus 1 plus 1 over n plus 1. We can't simplify this any further, all the way up till plus 1 over m. So all these terms will cancel out because, oh sorry about that, this should be a minus. So this n plus 1 will cancel out with this, and n plus 2 right here will cancel out with this. So and so on and so forth. There has to be a 1 over m minus 1 right here. So all these terms cancel out, and at the end we just get 1 over n minus 1 over m, which is less than 1 over n. And remember that n is greater than n. From right here we get that n is greater than n. So 1 over n is less than 1 over n, 1 over capital N, and we chose 1 over capital N to be equal to epsilon. So we get 1 over n is less than epsilon. So we have now shown that am minus an, after all this series of steps, we have shown that am minus an is less than epsilon. So therefore we have shown that this sequence is Cauchy, And since this sequence is Cauchy, from the previous theorem, every Cauchy sequence converges. So we have shown that it converges to a finite number, and we're done. So hope you guys have enjoyed this video. See you next time.